about rules for probability using theoretical probability. The example that we're going to consider is one that we've seen before, in which we roll two die. When we roll two dice, the sample space are all the possible outcomes for the two dice. So 1, 1, 1, 2, 3, 1, 6, 6. Okay, so 36 outcomes are listed here. We're going to consider the event E, which is a subset of the sample space, and the subset is just all the die in the sample space that have a sum of 7. That corresponds to these 6 outcomes. We can calculate the probability of this set E using the formula for theoretical probability, which is just the number of observations in the set E, which is 6, divided by the total number of outcomes in the sample space, which is 36. We get this number right here. So 16% is the probability. We're also going to consider the set F here, which is that the first die rolls a 3, so F is here, and those outcomes correspond to these outcomes in the sample space. Those are 6 outcomes, so again the probability is going to be 6 over 36 because there are 6 outcomes that correspond to event F. What's new is we're going to consider things that we can do with sets. So one thing that we can do with a set is an intersection that corresponds to an AND event, what satisfies event E and F. So the intersection is all the events in E that are also in F. And there's only one outcome in common, one way that set E and F can occur together, and that's the outcome of a 3 and a 4. Okay, so we can ask for the probability of E and F, or E intersect F, and is just 1 out of 36 because there's one event in common out of 36 outcomes, and it gives us this probability. Okay, another operation that we can do with sets is called the union, and that would be considered all the events in set E or in set F, and it corresponds to these events. Notice that set E has 6 events and set F has 6 events, but the union only has 11. That's because the intersection 3, 4 only gets listed once. Okay, so there's a formula for uh, OR events, and it's the general addition rule. The probability of A or B is the probability of A plus the probability of B minus the intersection, and here we have to translate that into E and F. So here I calculate the right-hand side. That is, I calculate the probability of E, the probability of F, and I subtract the intersection. That gives me this probability of 30.55%. Another way I can calculate the probability is just by counting how many things there are in E union F. That set has 11 outcomes divided by the sample space of 36. It also gives me 30.55% repeating. So it doesn't matter if I calculate it, the probability of E and F and subtract the intersection, or I count the elements in the union. They give me the same thing. Another thing that we should think about is suppose that we're ensured that the first die rolls a 3. Well, if the first die rolls a 3, that changes the sample space. So the sample space is everything here, but if we're ensured that the first die rolls a 3, this event 1, 1 isn't possible. This event 1, 3 isn't possible. This event 2, 6 isn't possible. We have to have only events where the first die rolls 3. Otherwise, uh, otherwise we're not ensuring that the first die would roll a 3. So a conditional probability changes the sample space, and it changes it to be exactly the set F. So the sample space is now the set of F, and we want to know how many ways can how many ways can we get a face value of 7 when we sum them? Well, that's exactly the intersection. So for a conditional probability, you're conditioning on an event being true, which is that the first die rolls a 3, and so that changes its sample space to the conditional. And then to calculate the probability of the set in question, we have to calculate the intersection. So that gives us this formula. The probability of A conditional or given B is the probability of the intersection divided by the probability of the conditional. For the dice, that gives us this 0.166. Should notice that this probability 0.166 is exactly what we got when we just calculated the probability of E. So the conditional did not change the probability. When we have that the conditional does not change the probability, the two events are called independent. So here the conditional probability of E, that the sum of the two die rolls is 7, is unchanged by knowledge of F, which is that the first die will roll a 3. In this case, since it doesn't change the probability, F does not affect E or vice versa. The two events are called independent. So specifically, if we have this equality, the two events are called independent. If they're not equal, they're called dependent. Now, an equivalent formulation of this conditional probability is just this, that the probability of E and F is the probability of E times the probability of F. One thing going back to the conditional probability formula is if we cross multiply, this tells us the probability of A and B is the probability of A given B divided by the multiplied by the probability of B. That's called the general multiplication rule. Okay. One last rule we're going to discuss, and something that you can do with sets, is called the complement. The complement of an event is the set of elements in the sample space that are not in the set E. That's denoted by E superscript C for E complement. Okay. In this case, the complement of the set E, these are all the events in the sample space that are not in E. Okay. And we have a formula for complements involving probabilities. That is, the probability of complement is 1 minus the probability of the set itself. And we verified this by calculating 1 minus the probability of the set, E, getting 0.833, and then just calculating the number of elements in the complement divided by the sample space. That gives me 0.833. So that's a numeric verification. So um, to summarize these formulas, what we've learned today is the complement rule given right here. We've been given and told how to verify if two events are independent, equivalently uh, dependent if the equality does not hold. We've been shown the general multiplication rule. We haven't been given an example. We've been given an example of conditional probability and using the conditional probability formula. And then there is the general addition rule. So a lot of stuff to write down and to think about. All these formulas are important. And let's not forget intersections and unions for sets. Thank you very much.